Okay, we talked about two different methods for volume. Here's our second method. We did slicing previously with our washer and our disc. Now we're going to be looking at shells, just because it's nice to have another method. Not everything fits in a nice little cookie cutter format, right? So it's good to have options when we're looking through these different problems. Now here's what's going on. I'm going to have shells. So we're talking about a cylindrical shell. So we have different shapes that we look at, and whenever we have this figure, we're going to take this one and we're going to wrap it around this y-axis, and around that y-axis we have this kind of bell-looking shape, right? Okay, here's the deal. Here's the moral of the story whenever it comes to shells. You are going to use this method. Let's write it down. Use this method when you go around the axis, but your equation is in terms of the other variable. Let's talk about that here for a but your equation is in terms of the other variable. So this is what we're talking about here. I have this function right here. This function is in terms of x. However, I'm going to go around the y-axis. So when your function is in terms of the other variable than the axis you're revolving around, and it doesn't switch over nicely, because like in the problems we did in the last section, we could switch those variables over nicely. But if it's not going to switch over nicely, that's where you use shells. All right, another method to still find volume. We're still finding volume on this. All right, so here's another figure. Just like we had that figure previously. I'm going to scoop this up so you can see it a little bit better. Here I have a bunch of cylinders. Before I had those circles over and over again. Here I'm having cylinders because I have to go this full length. So this whole amount of cylinders is what we're looking for. All right. So here's the other tip off. Whatever, ever, looks like two R's. That's what threw me off. Whatever axis your figure is sitting on. All right, that is the differential. And this is why the differential is so important. Whichever axis your shell, I'm going to say, I put figure, but I'm going to put shell because that's what we're talking about. So your shell, so your cylindrical shell is sitting on. So here for this one, I'm revolving around the y-axis, but do you see how I am sitting on the x-axis? That means I'm going to have a dx. Right there. So because I'm sitting on the x-axis, I'm revolving around the y-axis. It's the opposite for your differential. It's the opposite variable. All right? So everything up to this point, whatever the differential is, that's the axis you're revolving around. That's the variable that you're using. Now, whenever I'm using volume by shells, it's whichever axis my shell is sitting on. That is going to be my differential. All right. Okay. And I'm using shells. So let's kick it back to geometry a little bit here and let's talk about cylindrical shells. If I'm going to have this cylinder, right? So here's all these different cylinders. We're going up here and then around. This is my cylinder. If I slice this down the middle and I roll it out, then I have a rectangle, right? Okay, so here's the kicker. When I'm looking at a cylinder, we have this is a circumference of my cylinder, and that's this 2 pi r. That's what we're getting at. And our r, right, is how far away we get to our function. That's what's happening. That's why we're saying my radius here is this x sub k, because it's how far I get out there to my function. Then I also have a height, because this is a cylinder. The height of my cylinder is how far out, or, oh, I said that wrong. This is my x value. This is how I get to my function. That's the height of my function. It's how far out. Okay, so let's talk about this. Let's write this real quick. Surface area, because that's what we're looking at. We're just adding up a ton of surface area. 2 pi RH, because it's more than just this circumference. I also have to take into account my height. My height, let me squeeze this in a little bit. My height is what's going to go up here to my function. My x value that I'm looking at here, whenever I'm talking about my radius for this cylinder is going to be how far out before I get up to my height. So it's the x coordinate, how far out I get up to my height of my cylinder, which is going to be my actual function. My radius is the x coordinate and the x value. My height is going to be my actual function. All right? But whenever I'm talking about a cylinder, right, that's all we're looking at. A shell is going to be a cylinder, and I'm looking at my cylinder here. Okay, so let's put this, I ran out of room here. Let's go to this next page. So volume by the shell method looks like this. So if I'm going to look at my volume, that's going to go from A to B, of course, because we're talking about this x. So 2 pi RH. So 2 pi, and then my r we determined is that x coordinate, and my height is going to be the top function minus the bottom function. Now I could be, so this I'm going to write here is 2 pi r, and then this section right here is my h, because that's my cylinder. And we have infinitely many of those. And this is sitting on that x-axis, revolving about the y-axis. Sitting on the x-axis, revolving about that y-axis. All right, that cylinder, if I break out those cylinders. Now here, this is saying my top function minus my bottom function, and we're just putting this on here in case I have a bottom function. If I'm sitting on the axis, right, if I'm sitting on, then my bottom function is just going to be 0, because that's y equals 0. That's the x-axis that I'm sitting on. So it's not that big of a deal. All right, okay. So here, it's just my top minus my bottom. We're just taking care of that right up front instead of saying disk method, washer method. It's just still the cylinder. So what am I looking at here for my cylinder? Okay, whichever axis you are sitting on, that is your differential. Okay, let's do some examples then.